you see that? All right, thank you, Martin. After listening to all the talks today, I'm thinking I should have titled this one Yet Another malloc Implementation, but no, it's actually titled Flexible and Effective Object Tiering for Heterogeneous Memory Systems. So a little bit about me. I'm a fifth-year PhD student at the University of Tennessee in Knoxville. I work in the Courses lab under Dr. Michael Jantz. Courses stands for Compilers, Operating, and Runtime Systems, which is sort of where we focus our efforts to solve problems in the area of like program performance, analysis, and profiling, and things like that. We're lucky to have some really great collaborators at Oak Ridge National Laboratory, which is just down the road from us, and at Intel, so I'd like to give them a shout out. So in our really excellent keynote talk, Martin mentioned some seismic shifts in memory in the memory field. And I'd like to add one more to that, and that's the expanding variety of memory devices that we're working with these days. So recent architectures are adopting a combination of memory devices that have different characteristics and different performance features. So some examples of these are like high bandwidth memories, or non-volatile and persistent memories, such as the Optane, Intel's Optane DIMMs, and even something as bizarre as like disaggregated memories like the Compute Express link are being included on a single architecture, which is really interesting. And so this brings forth a new challenge for us as memory management researchers, and that's where we decide to place this data, and by where I mean which device, that has great impacts on an application's efficiency, and so that's a new challenge for us to solve. But this has been looked at before, right? And so here are some of the solutions that exist currently. One of them, if you're working with the Optane, is or any of Intel's memory devices, is to use something called memory mode, which basically takes your lower tier, and by lower tier I mean the slower device or less preferred device, and uses your upper tier as a hardware managed cache for it, right? So you get the capacity of the lower tier, but you get the speed when you hit the cache of the upper tier. So that's nice, but you sacrifice some capacity there. Another approach is to use page-based profiling and do some tiering automatically in the operating system. Linux has a couple of patches that do just that. Or you can take the option of using some user space code and extending the actual application to just do this tiering for the application there. So some options for that are HEMEM or SICM. SICM is the simplified interface for complex memory, and that is one of the earlier projects that our lab worked on with Oak Ridge National Laboratory. So these solutions are great, and we've tested some of them, and they work really well, but none of them satisfy all of the following criteria or goals, right? So like I said, the hardware-based approaches sometimes sacrifice total system capacity because you have to use one tier as a cache for the other. Some of them require modifying the application or modifying the operating system, recompilation and things like that, which sometimes can be intractable depending on your situation. A lot of them are not very flexible, and you don't have the user as an option to change the policies and decide how this tiering should be done. And some of them don't support exploiting the logical structure of program data in these tiering decisions. So we want to think about how the application is actually using this data rather than just looking at opaque pages. So our approach seeks to meet all of these goals, right? So what is our approach? Well, it's composed primarily of two software components. The first is a custom malloc implementation called bkmalloc. It is responsible for allocating these logical program objects, right? So their address and size mean something to the application. And once it does that, it communicates information about the object to a daemon, right? So it tells the daemon when these objects are created and when they're destroyed and other things like that. So this daemon is called MAT daemon, the memory auto-tiering daemon. It's responsible for maintaining records of all the objects that are alive in the application, profiling accesses to these objects, and then it enacts these user configurable policies that migrate the objects periodically, okay? So this diagram gives an overview that we'll just go through of how the system works. So bkmalloc is dynamically linked to the program with LD preload, so the application runs unmodified and just gets this new malloc implementation. When the application allocates objects, they are aligned on page boundaries, and their size is padded out to the next page so that we can use the NUMA subsystem to migrate them as a whole. And you might be wondering what happens when the application wants an object that's smaller than a page. Well, we sort of aggregate those into big page and line blocks and consider them as one object. So as I mentioned, the allocator then sends these records to the daemon, like every time there's a malloc or every time there's a free event, the daemon gets notified, and we do this through a standard POSIX message queue. And on the other side, the daemon creates records for these active objects. So at the CPU level, right, the application is using this memory and it's accessing these objects, and we use perf to sample these architectural events. We capture LLC misses, and why do we do that? Well, we want to know when these objects are being accessed on an actual memory device like DDR and PMM, the Optane that we used. And we want to know where these accesses were satisfied, right? Did they actually go to DDR or was it in the other device? We also use eBPF in the daemon to intercept these perf events, and they're relayed to the user space code in the daemon through a ring buffer. So that helps speed up that process a little bit. The daemon then takes these accesses and reflects them on the corresponding object record so that we maintain basically a usage profile of all the active objects in the application currently, right? And then finally, we need to actually execute some policies that make these tiering decisions. So these are flexible, and custom implementations can be provided so that you can do something like tune for a specific workload or make different trade-offs. And we need to actually enforce these tiering decisions, so we use the NUMA subsystem and move pages on the application's behalf, right? So we need the permission to do that from the daemon. Okay, so I've mentioned these policies a couple of times. The main thing to know about this is that they make two primary decisions for the daemon, and that's, the first one is, when do we want to actually migrate these objects, right? So for this study, we evaluated 3 different trigger migration policies, and the first one was a basic timer. So every n timer ticks, let's reassign object tiers. The second one is, we call it LLC MPI. It's the last level cache misses per instruction, and we try to look for spikes in this over some time window, and that's basically indicative of some kind of phase change. So we want to know if the application is changing what it's doing, and we'll reassign at that moment. And the third one is the allocation trigger. So after the application allocates, let's say 10 gigabytes, we want to trigger migration, and then on the next 10 gigabytes, we'll trigger migration again. So the second decision that we want to make in these policies is, how do we actually rank these objects and calculate how they should be prioritized for the upper tier? So again, we chose 3 policies to implement and evaluate in this study. The first one being FIFO, so first in, first out. And it looks at the timestamp of creation of this object, right? So newer objects are preferred for the upper tier and older are preferred for the lower tier. LRU was our second one, and that just looks at when these objects are actually being accessed. So recently accessed objects should be preferred for the upper tier and vice versa. And the final one is accesses per byte, and this is basically just a hotness scale. We're looking at how many accesses are we getting for the size of this object, and that's going to be indicative of how much accesses we're getting on it. Okay, so we evaluated this on an Intel Cascade Lake platform. We have 16 physical cores and 32 logical cores, and we did have hyperthreading enabled. We had 192 gigabytes of DDR as our upper tier, and our lower tier was a set of Intel Optane DIMMs, totaling 768 gigabytes. And we used the NUMA subsystem to basically identify these as separate NUMA nodes. This is the list of the workloads that we tested against. I'm not going to go through the list, but the key idea here is that these are all memory-intensive applications. They represent a few different fields like high-performance scientific computing, machine learning, and graph search. And we configured them to use about 400 to 600 gigabytes of peak RSS for our performance evaluation. And the idea there was we wanted to get well above our upper tier's capacity, right? So we would have to spill over into another device. But before we go into the performance analysis, I'd look at just the overhead of the system, right? We've added a bunch of different things into the system, and we want to know how those impact performance in general. So things like adding a new malloc implementation, what is the performance of that? We also chose to reserve 2 cores for the daemons so that it would be preferred in the scheduler and get work done in a timely manner. So we want to evaluate that. And as well, we're doing all this profiling with perf and BPF, and we want to quantify that. So here are some figures from the paper on this overhead evaluation. Some things to notice here. We noticed that taking 2 cores away from the application has very little effect on these programs. And we think that's because they're memory bound in the first place, so removing compute isn't going to have much of an impact. Likewise, our allocator doesn't really have much of an effect on performance, and on average case, it actually beats the system allocator, which is glibc. And as far as profiling costs go, the average case is about 3%, which is pretty good, but we're going to have to make that up with our performance savings. And the worst case is only about 6%, so easily doable. And then if we look at memory usage, how does all this affect memory? Well, on average, you can see we have very little effect at all from the allocator, but we do have some outliers. So we have about a 10% increase in memory usage for this benchmark, but 7% decrease for that one. So, but overall a wash. So how did we evaluate the performance of this system? Well, we compared those benchmarks with our daemon enabled versus a couple of approaches. The first one I want to talk about is first touch. And so this is basically the default behavior of your NUMA control system, right? So if you want a page, it's going to take it from the upper tier until the upper tier is full. And then once the upper tier is full, it will default to the lower tier. So that's first touch. We also evaluated against memory mode, which is that hardware cache-based solution. And then we also compared against those Linux tiering patches that does it in software. Now, we chose to use the best overall policy configuration for this experiment. We did a whole set of evaluations evaluating the different policies and combinations of them in the paper, but I won't go into that, so I recommend you check that out if you're interested in that study. Okay. So finally, these are the results from the performance evaluation. So the top graph is execution time relative to first touch, and the bottom is total amount of memory read over the course of the run. I'll get to that later. So what we see here is that all 3 of the approaches that we tested are significantly better than first touch, right? So pretty much doing anything at all is going to get you big gains over first touch. And we see that Matt Damon enables better performance than the other software-based approach on average, so that's great. Now, if we look at the amount of memory read over time, we see that some of our benchmarks use significantly less traffic over the course of the run than memory mode, which makes sense because this hardware approach is trying to maintain a cache the whole time, so it's swapping and copying memory back and forth. And so we argue that the software approaches can be better if you care about power efficiency in this case, right? Because that all costs power. Okay, so in conclusion, our framework enables a competitive application performance on these platforms compared to some of the other approaches, but it eliminates many of the limitations of the other approaches, which we find really nice. And since you can enable your own policies very easily, it lets you tune for your specific use case, which we think is great. So I'd like to thank everybody that's involved in organizing this conference, and thank you for listening. And I'd like to thank also Zach McMichael, who's the second author on this paper, who's here today. So with that, I'll take any questions.
All right, any questions? I'll start and go.
Okay. Thank you for the talk. A couple of questions. So one is, what, if any, changes would you need to make if you wanted to extrapolate this to more than 2 levels of a hierarchy? So the examples you showed were for DRAM and then the NVRAM beneath. What if you wanted to, say, include this to take care of software-managed scratch pads above the DRAM? Would you need to make any changes there?
So I personally would have to make a few changes just to the way the daemon works, but that's just because I didn't write it with that in mind. But the application wouldn't have to change. The policies wouldn't have to change. And the changes that I would have to make are just in a user space application, so they're trivial to implement and deploy.
Okay, could you succinctly say what those changes in the user application would be?
Just that the code is written with the assumption that there are 2 nodes.
Okay.
That's it. Yeah.
And the other question I had was, are there any restrictions on the user space policies, or can the user basically put whatever they want policy-wise in
They
there?
can put whatever they want in there. They just need to answer those 2 questions for the daemon, essentially.
Okay, thank you.
It's always a bit guilty asking questions at the last paper. Let me do this quickly.
No worries.
So assuming you have perfect information, run your benchmark twice, for example, do you have a measure what's the best the system can do as a way to measure how much additional room that you may improve? And I also think that's useful for the user to figure out whether he wants to try more.
So we don't have a system to do that. We've definitely worked with similar approaches that use offline profiling, and those can certainly perform well, but our recent study, that SICM project, has shown that the offline profiling can do just really close to just about as well as the offline profiling. So you can get really close, actually. But I don't have any numbers as far as how close we are to optimal. Yeah.
Any more questions? So I guess I have one as well. So it looks like there is a synchronization point when the allocator calls into the kernel.
Mm-hmm.
And so if you have a larger number of processes, how does that affect the performance, if at all?
So calls into the kernel. What do you mean by calls into the kernel?
So in the early slide where you had the allocator, there is a
Sorry.
yeah, or where it calls to the daemon.
Sure.
Yeah. So is there a synchronization overhead in that place that might be a scalability bottleneck with large numbers of processes?
We measured the overhead on our platform with I guess 32 processes and didn't find any significant overhead for that messaging. Yeah.
Yeah, that sounds great. Thanks.
Yep.
All right. No more questions. In that case, let's thank the speaker once again. And that concludes our session. And with that, I'll hand it over to Eris for closing remarks.
So thank you everybody for coming, and see you next year in ISMM'24.